Hello, my name is David Blewett. I'm a lunar and planetary geologist in the Moon and Rocky Planets group at the Johns Hopkins Applied Physics Laboratory. An often overlooked fact about the Moon is its seismicity. The Moon is seismically active. Seismic activity on the Moon was sensed by the Apollo passive seismic experiments, which consisted of seismometers that measured the horizontal and vertical components of the Moon's surface motion. These stations were all on the near side. The network operated until 1977 and measured more than 12,000 seismic events. The amount of energy released in moonquakes is much less than that of the Earth, but nonetheless, design of permanent settlements or other infrastructure will need to consider the occurrence of moonquakes. The quakes have been placed into four classes: deep, thermal, impact-induced, and shallow. Deep moonquakes are the most common, suspected to be triggered by tidal forces generated by the gravitational interaction of the Earth and the Moon. Deep moonquakes are unlikely to represent a risk to structures since the largest body wave magnitudes are below 3 on the Richter scale and occur at depths of 700 kilometers or more. Similarly, thermal moonquakes are of low risk since they have the smallest amplitudes. Thermal moonquakes are caused by the expansion and contraction of the lunar near surface due to temperature variations associated with the day-night cycle. Meteoroids and artificial impacts, spacecraft, can also induce moonquakes, with variable amplitude depending on the speed of the impactor and its distance from a seismic station. Vibrations due to the impact of larger projectiles can produce substantial ground motion amplitudes, which can be hazardous to structures. Finally, there are shallow moonquakes, which have the largest amplitudes. Shallow quakes result from slippage on existing faults or by the formation of new thrust faults, all related to the Moon's global contraction. While relatively rare, the associated body wave magnitudes for these events can be 5 or greater on the Richter scale and can have stress drops of up to 100 megapascals. As such, shallow moonquakes could cause damage to a lunar base and must be considered for habitat and other surface structure designs. Seismic signals on the Moon are characterized by a gradual beginning, a broad maximum, and a very long decay, lasting up to an hour. Now compare this to just a few minutes decay time on the Earth. Thus, the scientists first studying the Apollo data said that the Moon rings like a bell. The long duration is a result of the low attenuation and intense scattering within the highly porous and fractured lunar interior, especially the upper regolith. The nature of the seismic waveforms is expected to produce sustained loads on surface structures. Overall, the main challenge associated with moonquakes is the limited information we have about them. The Apollo passive seismic experiment consisted of just a few stations that covered a relatively small area of the near side. The far side remains largely unexplored. Although a PRISM payload, the Far Side Seismic Suite, is planned for an upcoming delivery to the Far Side Schrödinger Basin. The intense scattering makes it difficult to precisely read arrival times of seismic phases, resulting in poorly constrained models of the inner structure. Seismic hazard analysis that considers site terrain and the nature of the lunar subsurface could help to mitigate threats to surface assets arising from moonquakes. An example of such an analysis is shown on the right for the Taurus-Littrow Valley, the landing site of Apollo 17. This area includes both ancient highland and younger volcanic Mare basalt terrain. The model evaluated the ground surface amplification pattern in both the vertical and horizontal directions caused by a shallow moonquake and by a meteoroid impact in this region. The findings are that surface wave propagation leads to high surface displacements in the center of the valley, with lesser amplitudes at the valley edges. Models like these can help to prepare structures and systems for potential seismic effects, particularly for sites with high relief or steep topography that will experience very complicated surface wave interactions. In combination with landing site hazard modeling, the best mitigation for moonquakes is to design structures that are resilient to seismic events following guidelines similar to those for terrestrial builds. Finally, qualification test campaigns for systems that need to be stable on the lunar surface should include tests that consider stresses induced by shallow or impact moonquakes. This is particularly important for systems planned for a long stay on the Moon. Thanks for watching, and I hope this module has been informative.